Balloon 4-3 Weather Theory and Reports. Let's explore the fascinating dynamics of convective currents, those upward-moving streams within convection circulation, akin to thermals or updrafts in cumulus clouds. The Earth's diverse surfaces, each radiating heat in varying amounts, give rise to local circulation zones. Plowed ground, rocks, and barren land emit substantial heat, while water bodies and vegetated areas absorb and retain it. Picture this as nature's ballet, where convective currents choreograph bumpy, turbulent air, often encountered during low-altitude flights in warmer weather. In regions with adjacent land and large water bodies like oceans or lakes, the intensifies. In daylight, land heats faster, creating warmer, less dense air that rises and gets replaced by cooler, denser air flowing in from over the water, a phenomenon known as a sea breeze. Come night, land cools swiftly, prompting warmer air over the water to rise and be supplanted by cooler, denser land air, a nocturnal ballet named a land breeze. These intricate movements unfold anywhere there's uneven heating of the Earth's surface. For pilots navigating close to the ground, convective currents add an extra layer of complexity. On final approach, the rising air over barren terrain can induce a ballooning effect, potentially causing overshooting of the intended landing spot. Conversely, approaches over water or dense vegetation may trigger a sinking effect, posing the risk of an undershoot and a potential encounter with obstacles like trees or power lines. Now, let's touch upon the jet stream, a high-altitude, narrow band of strong winds. While it primarily captures the interest of high-level flights, its position, strength, and orientation closely tie to broader weather patterns, shaping the ebb and flow of atmospheric conditions. Transitioning to local and small-scale winds, gradient winds kickstart air movement, aligning with the pressure gradient force and the Coriolis force. This sets the stage for parallel movements along curved isobars, creating a delicate balance. Orographic winds, influenced by terrain like mountains, showcase the effects of upward deflection or daytime heating-induced updrafts. Anabatic winds, an upslope flow, ascend steep slopes during calm, sunny days, driven by the sun's warming embrace. Conversely, katabatic winds, nocturnal and downsloping, unfold as ground-level air loses heat faster through radiational cooling compared to the surrounding landmass. In this atmospheric theater, these winds and currents play starring roles, influencing flight dynamics and shaping the symphony of weather patterns. Gazing up at the sky, clouds are like Mother Nature's storytellers, revealing tales of air movements, moisture, and the delicate balance in the atmosphere. They're like weather signposts, offering insights to the discerning balloon pilot. Picture them as nature's canvases, slow dancing in the sky at a leisurely pace of 1/10 of a mile per hour. But as captivating as they are, too many clouds or the wrong kind can turn into a weather puzzle for balloon enthusiasts. So what are clouds, really? They're the visible result of moisture getting cozy in the air, forming droplets of water or crystals of ice. Carried along by gentle breezes, clouds are born from of slow air movements, painting the sky with their unique patterns. But when these patterns get too crowded, hang too low, or grow too big, they can spell trouble for balloon adventurers. Clouds tell a weather story, but pilots need to be fluent in cloud language. Understanding cloud types helps pilots decode weather reports and get a feel for what's happening up there. Clouds come in various forms: low, middle, high, or with vertical development. It's like they have their own cloud neighborhood, each type with its distinct height, shape, and behavior. The International Cloud Classification is like the cloud community handbook. It sorts clouds into low, middle, high, and those with vertical development. Knowing these classifications is like having a guide to deciphering the sky's language. There's a whole vocabulary: cumulus, stratus, cirrus, castellanus, lenticularis, nimbus, fracto, and alto, all these clouds with their unique personalities. Low clouds are the ones close to the ground, like stratus and stratocumulus. They're a bit moody, changing quickly and creating low ceilings that can mess with visibility. If they form below 50 feet, they're basically fog, making it tricky for pilots to spot landmarks and landing fields. Moving up the cloud ladder, middle clouds hang out between 6,500 and 20,000 feet. They're like altocumulus, altostratus, and nimbostratus clouds, fancy names for clouds with water, ice, and supercooled droplets. They bring a bit of turbulence and icing to the party, influencing flight plans and hinting at not-so-great weather. Then there are the high clouds, chilling above 20,000 feet. Cirrus, cirrocumulus, and cirrostratus clouds are like the cool kids of the sky. They form in stable air and might not be a big deal for balloon pilots, but they often drop hints about future weather changes. Imagine clouds as storytellers in the sky, revealing tales of air movements, moisture, and atmospheric balance. Among them are cumulus clouds building vertically into towering cumulus or cumulonimbus clouds. It's like they're reaching for the skies, creating a spectacle that can sometimes turn into thunderstorms. These clouds bring a touch of drama to the atmosphere, with bases forming in the low to middle cloud region but extending their influence to high altitudes. When you see towering cumulus clouds, it's a sign of atmospheric instability and the air around them gets a bit turbulent. These clouds usually set up shop below 6,000 or 500 feet, but their tops might stretch above a whopping 60,000 feet. What's the secret behind their towering presence? It's all about lifting action, convective currents, orographic lift, or frontal lift that gives them their grandeur. Scattered cumulus or isolated cumulonimbus clouds are usually easygoing companions for balloon pilots as they can be navigated around without much hassle. But here's the catch. They can swiftly gather into groups or lines, evolving into a cumulonimbus congregation. Sometimes they play hide-and-seek within stratiform clouds, creating tricky flight conditions. Now let's dive into the cloud neighborhood. There are two main subdivisions within the high, middle, and low cloud groups. First, you have cumuliform clouds, the ones that look lumpy or billowy, showcasing their vertical development. They bring turbulence, making flying conditions a bit bumpy. On the flip side, there are stratiform clouds, those layered-out clouds that usually promise a smooth flight. And here's an interesting addition to the cloud lexicon: nimbus, meaning rain cloud. These are the clouds that bring heavy precipitation, either in liquid or solid form. So when you hear about nimbostratus or cumulonimbus, it's like a weather alert saying, hey, get ready for some rain or a thunderstorm. Speaking of thunderstorms, cumulonimbus clouds are like the rock stars of the cloud world, containing loads of moisture and unstable air. They're known to throw a wild party with lightning, hail, tornadoes, gusty winds, and wind shear. These towering clouds can be a bit mysterious, sometimes hiding behind other clouds. When that happens, they're called embedded thunderstorms. For pilots, cumulonimbus clouds are the rock stars you'd rather avoid. They can appear solo or in groups, creating either air mass or orographic thunderstorms. The Earth's surface heating causes air mass thunderstorms, while the upslope motion of air in mountainous regions leads to orographic thunderstorms. Cumulonimbus clouds forming a continuous line are like non-frontal bands of thunderstorms or squall lines, nature's way of turning up the drama. Understanding cloud types and their nuances is like having a backstage pass to the weather show. It helps pilots visualize what to expect and identify potential weather hazards. It's a bit like knowing the characters in a play, each with its own role in the atmospheric storyline. Now let's talk about ceilings and visibilities, the supporting actors in the sky drama. The ceiling is like the opening act, setting the stage with the lowest layer of clouds reported as broken or overcast, or the vertical visibility into an obscuration like fog or haze. Think of it as the celestial dome, where cloud coverage is reported in octals from scattered clouds, 5/8 to 7/8 coverage, to overcast skies, the whole sky covered. Visibility, our supporting actor, is the distance at which you can spot prominent objects with the naked eye. It's like the script that tells you how far you can see. Prevailing visibility is the key player, indicating the greatest horizontal distance over which objects can be seen and identified over at least half of the horizon. It's reported in statute miles, giving pilots a sense of how clear the view is. So the next time you look up at the sky, remember it's not just a canvas of clouds. It's a dynamic performance, with each cloud type playing its role and ceilings and visibilities setting the scene for the atmospheric play.